semiconductor devices. So before going to our topic, let us see different types of appliances which we use daily. So look at these appliances. So we have two different types of appliances here. So one is electric appliances and the other is electronic appliances. So where we use, what is the difference between these two? So the electric appliances, they will do particular task, that is they will simply convert one form of energy into the other form. If you take for example a light bulb, okay, so it converts the electric energy into light energy. One more example is fan. Fan converts electric energy into mechanical energy, it rotates, right? So there is no smartness is involved in electric appliances. Whereas electronic appliances, if you take a mobile, the laptop, PC, digital camera, all these are electronic appliances. So if you take a mobile phone, you can do many things using mobile phone. So you can record videos, you can take pictures, you can send text message, you can make a call, and many more things can be done using a mobile phone, right? You can watch TSAT live programs also. So these all things, that means in these two appliances, which is smarter? Obviously the electronic appliances, right? So what is making these electronic appliances much smarter? So it is the components which are present in electronic appliances. So we will see what are the appliances present in electronics. So these are the components present in electronic appliances. There is a resistor, capacitor, diode, and we have rectifier and light emitting diode and integrated circuits. Okay, these are all the electronic components. So if you see in all the PCs, personal computers and mobile phones, we have this integrated circuits. Have you ever dismantled or disassembled your mobile phone? Yes. Have you ever seen the choke of your tube light? So what are all there in that? So we have electronic components in choke of your tube light. If you see, there are diodes, there are resistors, capacitors, and all these components are there in a choke of tube light. And if you see in your mobile phone, you will have a processor. Okay, it will be same like this integrated circuit. If you see this integrated circuit, it is rectangular in shape, but if you see in mobile phone, maybe it is in square shape. Okay, so if you have observed motherboard of your personal computer, there will be a processor. Okay, so if you see the specifications, where the processor specifications are mentioned, you see the specifications in your mobile phone. So in settings, you go for specifications. There will be CPU. So CPU, it will be quad core processor or octa core processor. Okay, those processors are made up of semiconductors. So the electronic components are made up of semiconductors. So why we are going for semiconductors? What is the main property that is making semiconductors useful in electronics? We will see. So what is a semiconductor initially? So a semiconductor is a material which has conductivity in between conductor and insulator. So in periodic table, you can observe the elements are divided into conductors, insulators, and semiconductors. So most of the metals are conductors, and there are semiconductors also. The 14th group are semiconductors, and all the ideal gases which have their valency 8 valence electrons, they are insulators. So other property of one of the property of semiconductor is it has a negative temperature coefficient of resistance. That means it has if temperature goes on increasing, if temperature increases, the resistance of semiconductor decreases. So this is called negative temperature coefficient of resistance. So temperature, as temperature increases, resistance decreases. Okay, this is one of the property of semiconductor. So we will see what are the examples for semiconductors. If you take the 14th group of elements, so we have silicon, germanium. In 14th group we also have carbon, silicon, germanium, and we have tin. Okay, so and some of the compounds, that means if you mix two materials, gallium and arsenide, so they also make very good semiconductor. So gallium arsenide, and we have indium phosphide, gallium phosphide. So these are all the examples for semiconductor. So we will see the structure of the differences between the conductor, insulator and semiconductor. So see the slide. We have in conductor we have valence band and conduction band. So any element will have a valence band and conduction band. So the conduction band and valence band of conductor are overlapped. That means there is no gap between valence band and conduction band in case of conductor. Whereas for insulators, the gap between valence band and conduction band is very high. Okay, it is about 5.5 electron volts or more. Okay, so that band gap for semiconductor, it is very less. So it is about 1 electron volt. So the differences between these semiconductors, conductors and insulators is because of the valence electrons. So if you see, conductors will have 1 or 2 valence electrons. Semiconductors will have 4 valence electrons. Whereas insulators will have 8 valence electrons, almost filled valency. Okay, that means they are stable. So the energy gap between the valence band and conduction band for conductors, it is 0 electron volts. That means they are overlapped. For semiconductors, it is around 1 electron volt, and for insulators, it is above 5 electron volts. So it is above 5 electron volts. Okay, so this is making the difference. So here insulators will not conduct electricity, and conductors, they will allow electricity, whereas semiconductors, you can make them, the conductivity of semiconductor can be varied. You can make them act as a conductor, you can make them act as an insulator. Okay, this is the property of semiconductor which is making it useful for electronics. Okay, electronic appliances, most of them are made up of semiconductors, because the conductivity of semiconductors can be varied. Okay, so that is the property which is making it useful for electronics. So in semiconductors, we have seen there are different types of semiconductors. Silicon is there, germanium is there. Okay, tetravalent elements are carbon, silicon, germanium and tin. Okay, so in all these we will use silicon the most. So why we use silicon the most is, there are number of reasons why we use silicon. So if you see the slide, the silicon is most abundant element in Earth's crust. That means compared to germanium. So it is the second most available element on Earth's crust. So that is why it is in the form of sand. Okay, so it is in the form of SiO2, silicon dioxide. So silicon dioxide is nothing but sand. Okay, so we can see sand everywhere, right? So it is most available. So you can extract silicon from silicon dioxide, whereas germanium, it has the germanium ores are less available. Okay, those are not that much available as silicon. So if you want to extract germanium, you have to go for ores of some of copper ores and silver ores for germanium extraction, okay, which is very hectic process. So silicon is most abundant. And one more property of silicon is it is less temperature sensitive. So as silicon has the energy gap of silicon is 1.1 electron volt, whereas for germanium it is 0.72 electron volts. Although the energy gap of germanium is 0.72 volts, which is lesser than the silicon, this we use silicon the most because the germanium is more temperature sensitive. So germanium is more temperature sensitive in the sense, for higher temperature it behaves the other way, and for lower temperatures it behaves in the properties of germanium will change. Okay, whereas for silicon it is less temperature sensitive. That means it will not react that much to temperature. Okay, so that is why we use silicon. And one more property of silicon which is making it more useful is ease of making oxides. So oxides of silicon can be formed very easily, that is silicon dioxide, and this silicon dioxide acts as perfect insulator. If you see IC fabrication, silicon atom will be there, silicon crystal will be there, and above that you will place a silicon dioxide layer which does not allow any other materials to interact with the silicon crystal. Okay, so silicon dioxide acts as a perfect insulator. So for that purpose, and you can make silicon dioxide very easily. So ease of doing oxides, ease of forming oxides also makes silicon more useful. Okay, so if you take silicon structure, we will see silicon structure. Silicon has 4 valence electrons, that is tetravalency. So if you take there are, let us consider this is a crystal of silicon. So each silicon atom has 4 valency. Each silicon atom has 4 valency. So to become stable, these atoms, silicon atoms, will form covalent bond with the adjacent silicon atoms. That means these 4 electrons will form covalent bond with the adjacent silicon atoms. So that the valence of each silicon atom will become 8. Okay, so 8 valency is stable one, right? So if valence electrons are 8, then it is said to be stable. Okay, so these silicon atoms will share the electrons. Covalent bond means sharing of electrons. So this will share the electrons with the adjacent atoms and will form 8 electrons and will be stable. So the pure silicon structure, the pure solid state of silicon structure crystal will be like this. So it will share the valence electrons with the other adjacent silicon atoms and they will form a stable structure. Okay, so this type of semiconductor is called as intrinsic semiconductor, that is pure semiconductor. A pure semiconductor is called as intrinsic semiconductor. So the conduction in this intrinsic semiconductor is due to temperature. Actually at absolute 0 temperature, this semiconductor acts as a perfect insulator. At absolute 0 temperature means, absolute 0 temperature is nothing but 0 Kelvin. Okay, so that is nothing but minus 273 degree centigrade. So at this temperature, this silicon will act as a perfect insulator. When the temperature increases, this electron will gain the energy to move out of the covalent bond. So, the electron will gain energy to move out of covalent bond. So, that will be free for conduction. So, when it is out of covalent bond, it will be free for conduction, and when it is left, there will be a void created from where it is left. Okay. So, it is left from here, from this covalent bond. So, there will be a void or hole from where it is left. So, this hole, the number of holes and the number of electrons in pure semiconductors are equal, because whenever this is left, there will be a hole, and if this electron goes and disturbs others, otherwise one electron is left from here, so there will be a hole here. So, number of electrons will be equal to number of holes in case of intrinsic semiconductor, and this is happening, this moving the electrons moving out of the covalent bond is happening when the temperature is increasing. At 0 Kelvin, there are no free electrons and free holes. When the temperature increases, when the temperature is increasing, then these electrons are moving out and for going for conduction. Okay. So, but these pure semiconductors are not used in electronics. So, what are used then? We use extrinsic semiconductors, that is impure semiconductors. We are adding other materials to the semiconductor to make, to improve or increase the conductivity of semiconductors. So, there are two, so thus the semiconductors are of two types, intrinsic and extrinsic. If you see, so pure semiconductors are intrinsic. So, the conduction in pure semiconductors is due to temperature, that means thermal conduction. And we have another type of semiconductors, those are extrinsic. So, that there the conduction is due to impurity atoms. So, whatever the materials we are adding to the pure semiconductors, those materials will make the conductivity improve. Okay. So, adding those types of materials, so we will add mostly the trivalent materials or the trivalent elements or the pentavalent elements to the semiconductor. So, adding these materials to the semiconductor is called as doping. So, we are doing this one deliberately. Okay. So, we are doing with an intention to increase the conductivity of semiconductor. So, intentional addition of impurity atoms is called as doping. So, if you see, you will add the impurity atoms intentionally. Okay. So, to the pure semiconductor to improve the conductivity of the semiconductor, pure semiconductor. So, what are two different types of impurity atoms are, we can add a trivalent atom, for example boron, aluminum, gallium, these all are trivalent atoms, right. They have 3 valency. So, boron, aluminum, gallium are 13th group of elements. So, they will have only 3 valency. So, if you add these type of elements to the pure semiconductor, then we call that semiconductor as p-type semiconductor. And you can also add 5 valency atoms, those are phosphorus, arsenic and antimony. So, those have 5 valency pentavalent atoms. So, if you add that type of atoms to the semiconductor, then that type of semiconductor is called as n-type semiconductor. So, there are 2 different types of semiconductors, extrinsic semiconductors. So, p-type semiconductor and n-type semiconductor. In case of p-type, you are adding trivalent atoms, and in case of n-type, you are adding pentavalent atoms. So, how the structure is going to change when you add p-type material and when you add n-type material. So, if you add a trivalent impurity like boron, so if you add boron, so the 3 valence electrons of boron will form covalent bond with the adjacent silicon atoms. So that means what? One more electron is needed to complete the covalent bond, to complete 8 valence electrons. Okay, so there will be a need for electron, that is called as hole. So this hole will accept electron from outside to complete this covalent bond. Okay, so that means what? P-type impurity can be called as acceptor impurity because it is accepting electron. So p-type impurity is called as acceptor impurity, and it will accept electrons, and if you add millions of boron to the silicon crystal, then millions of holes will be present. Millions of holes will be, this type of structures will be present. So these all will accept the electrons, which makes conduction possible. Okay, so if you take n-type semiconductor, if you see n-type, so you will add pentavalent impurity, that means 5 valence electrons are there. So in this we have added antimony, that is Sb. So in Sb, the 4 electrons, we have 5 electrons as valency, the 4 electrons of antimony form the covalent bond with the adjacent silicon atoms, and 1 electron will be free. Okay, so 1 electron will be free, so that free electron will be used for conduction. So as this material is donating a electron, okay, here boron is accepting electron, that is why we have called it as acceptor impurity. Here in this antimony is donating electron, so we call this as donor impurity. And as this hole is accepting electron, we say that hole is of positive charge, so that is why it is p-type semiconductor, and this antimony is donating a electron, so that is why it is called as donor impurity, and electron has a negative charge, that is why it is called as n-type semiconductor. So p-type, in p-type semiconductors we have holes as majority carriers, and in n-type semiconductor we have electrons as majority carriers. So if you see, if you make this p-type semiconductor and n-type semiconductor to come together, okay, so if you make these two crystals come together, these two type of semiconductors come together, then that will form a basic electronic device that is called as p-n junction diode. So this p-n junction diode, in this p-n junction diode we have made a p-type material and n-type material to come together. So the junction where this p-type and n-type will meet is called as p-n junction. So in p-type material you will have holes, right? We have seen in the previous slide that boron has holes, it is contributing holes to the semiconductor. So here the white ones are holes, p-type semiconductor the majority carriers are holes, and in n-type semiconductor the majority carriers are electrons. So this n-type is consisting of all pentavalent impurities. Okay, so when this junction is formed, when we made them come together, then diffusion process takes place. So what do you mean by diffusion? So diffusion is process of moving these electrons to the lesser concentration place. That means in n-type we have electrons, and in p-type we have holes as majority carriers. Okay, so in p-type the number of holes are more. Okay, we have number of holes, whereas in n-type you have less number of holes. Okay, so there will be a concentration gradient when you join this p-type and n-type materials. So because of this concentration gradient, so the holes from p-type will move to n-type and the electrons from n-type will move to p-type. So what happens? So this is n-type, let us consider. So, this is p type. There are electrons here and there are holes here. Holes are nothing but acceptor impurity. Holes are nothing but acceptor impurity. We have seen earlier that boron is acceptor impurity, and let us consider this n side. N side we have electrons, extra electrons, free electrons are due to the pentavalent atoms. So, that is antimony. Okay, antimony is contributing extra electrons to the semiconductor. So, this side, this is Sb electron. Wherever electron is present, free electron, you consider it as a pentavalent impurity, that is Sb, antimony. And wherever hole is present, you consider it as a boron. Okay. So when the electrons are more in this region and electrons are less in this region, these electrons will diffuse this side. Okay. So, the electrons will diffuse this side. When electrons leave this parent atom, when these electrons leave this parent atom, what happens? So, this becomes positive. Okay. So, this becomes positive, and these electrons will come here and will join this they will fill these holes. So, what happens? This boron will accept the electron. So, what happens? This becomes negative. So, whenever the diffusion process takes place, these positive ions are aligned here at the n side and negative ions are aligned here. Okay. So, we have negative ions aligned at the p side and positive ions aligned at the n side. So, this region, yes, this ionic region is called as depletion region. At this region, you do not have any charge carriers, right. So, there are no charge carriers in this region, they are stable ions. So, this region is called as depletion region. This diffusion will stop somewhere. Why? Because the electrons, as they want to move, as they want to diffuse to p-type material, they will be repelled by these negative ions. So, the depletion region will be constant. For silicon, it is about 0.7 volts, and for zircon, so there is ions formed at the junction, right. So, the negative ions are formed at the p-type and positive ions are formed at the n-type. So, positive ions are due to the left, that means the electrons are leaving the parent atom, that is why positive ions are formed here, and this p-type material, they are accepting the electrons, that is why they have formed negative ions. So, this region is called as depletion region because there are no charge carriers in this region. So, this region is depleted of carriers, and having this negative ions and positive ions aligned, this will form potential. So, this potential is called as barrier potential. So, this is about p-n junction diode when there is no external voltage applied. When there is no external voltage, we have not applied any voltage here, right. So, we have not applied positive or negative voltage to the p-type or n-type. So, in this case, at the instant where the p-type and n-type materials are joined, this barrier potential is developed. So, when you apply a voltage, then what happens? There are two conditions where p-n junction can be biased or applied voltage. So, those are forward bias and reverse bias. So, in forward bias, you apply positive terminal to the p-type and negative terminal to the n-type. So, when you apply like this, what happens? This positive terminal will repel the holes in the p-type, and this negative terminal will repel the electrons in the n type to the other side. So when this voltage is more than the barrier potential, the barrier potential you have seen in silicon it is 0.7 electron volts and in germanium it is 0.3 volts. When the voltage applied here exceeds that value, when it exceeds that value 0.7 volts, these electrons will gain energy to cross the barrier and will move to this positive terminal. They will be attracted to this positive terminal, so they cross this junction. Okay, so they cross this junction and will move to the other side. And when you apply in reverse, that means negative terminal is applied to p type and positive terminal is applied to n type. So when you apply voltage like this, these holes will be attracted to this negative terminal and these electrons will be attracted to this positive terminal. So they will move towards positive terminal, electrons will move towards positive terminal, thus they will increase the barrier. So the stable ions formed will be increased. So they will not try to cross the barrier because the positive terminal is here. Okay, so they will try to move away from the barrier. So thus the barrier will be increased. So if you see, there will be current flow in case of forward bias, whereas there will be no current in case of reverse bias. That is why this PN junction diode is also called as unidirectional device. That means it is allowing in one direction it is allowing the current and in other direction it is not allowing the current. So this in this case in forward bias it is acting as a closed switch, that is short circuit, and in reverse bias it is acting as open switch, which is open circuit. Okay, this is short circuit and this is open circuit. So have you ever seen the semiconductor labs? Yes, have you ever seen the semiconductor labs? How they will look like? So they will look like this. So these are not the doctors who are treating corona patients, they are semiconductor lab workers. Okay, so why they have wore mask? Why they are wearing mask? So why? Because we have seen doping process, right? So in doping process we need to add the impurity atoms into the silicon structures. So we will use different types of methods for adding impurity atoms like ion implantation. Okay, these all things will happen at higher temperatures. Those impurity atoms has to be added uniformly over the crystal. So for that purpose you need to make it in high temperatures. You need to add them in high temperature so that they will settle down, and you need to add the silicon dioxide layer, and these are all happen, they will all be made in using machines. Okay, so why? When they will contact with the chemicals. Okay, so that is why they are wearing masks. Okay, the elements, they are dealing with the dangerous elements, so that is why they are wearing masks. And if you see the applications of diode, we have seen that the diode acts as a switch. So in forward bias it acts as a closed switch, and in reverse bias it acts as a open switch. Okay, that means it is open. So and there is one more application of diode, that is it is used for rectification. So what do you mean by rectification? In our homes we have our power sockets, right? We charge our mobile using a power socket. So how much voltage is coming to our device? Actually at the power socket, if you put our charger, there will be 220 volts of voltage coming to that power socket, right? But that 220 volts is not used by all devices. Okay, our mobile phone will some voltage, and our fan will use some voltage, and our bulb will use some voltage. If you see, the bulb rating will be 6 volts or something. Okay, the 220 volts will not be used. So how the 220 volts is decreasing? So we are using a step down transformer there. So, step down transformer converts the coming alternating current, 220 volts of alternating current, into the rating whatever the device is using, the rating of the device. If it is 6 volts, then it will convert into 6 volts of AC. So, if the device is using a direct current, then there is a need of converting alternating current into direct current. So, that is done by a diode. So, if you see the slide, we have AC input here, and this one is a step down transformer. So, if you apply a 220 volts, let us consider like in our daily life only. Okay. So, in power circuit, let us consider this is power socket. So, we are having 220 volts of input here, and our device is using, let us consider there is a mobile phone here. Mobile phone is using only 5 volts of voltage. So, you need to convert this 220 volts of alternating current into 5 volts of alternating current first. Okay. That is done by a step down transformer, and afterwards this 5 volts of alternating current, that is it has 2 directions. So, this is applied to a diode. So, when you apply an alternating current to a diode, what happens? When positive half cycle is applied, this diode will be forward biased, because positive is applied to positive. So, it is forward biased, and the diode will act as a closed switch, and whatever input you are applying here will come to output. And when you apply negative half cycle, this diode will be reverse biased, because negative is connected to positive. So, this will be reverse biased, and this will be open circuited. It acts as an open switch in reverse bias. So, the diode will not allow the input to flow to the output. So, what you are making here, you are allowing only the positive half cycles to move to the output. Okay. That means at the output you will get only positive half cycles. You are converting, in the sense you are converting this alternating current into direct current. So, this is called as rectification. So, diode acts as a rectifier. Rectifier means it is converting alternating current into direct current. So, previously this diode, that means diode acting as a switch, and it is used for rectification. It is based on the control of electrons. This the application of diode, the switch, is done by vacuum tubes. That means the switches are developed using vacuum tubes. So, when you want to build a computer using vacuum tubes, it used to occupy a large space. It is about one room. Okay. So, but now what happened? The semiconductor materials has made the size of electronic devices diminish. That means we are using our computer, it is about 15 inches, right? Previously it was about one room space. Okay. But the main advantage of semiconductor is that only, that is decreasing of size of electronic devices. So, if you see, we have studied what we have differentiated the electronic devices and electric devices. Okay, we have known the differences between those two. Electric devices have done only one conversion of one form to the other, and electronic devices have done many things. So, the smartness has come from the electronic components which use semiconductors, right. So, we have seen the basic semiconductor device, that is diode, and in diode we have two types of materials, p type and n type. So, adding those impurities to the semiconductor is called as doping, and we have seen the application of diode. So, it acts as a switch and it also acts as a rectifier. So, we will see questions based on this. So, the question is, number of valence electrons in a silicon atom are. So, In silicon atom, what is the atomic number of silicon? What it is? So it is 14. Okay, silicon has atomic number as 14. So what is the electron configuration? It is 1s2, 2s2, 2p6, 3s2, 3p2, right. So the outermost shell electrons are called as valence electrons. So electrons, the silicon will have 4 valency, because in third shell are these shells are called as K, L, M shells, right. So in M shell we have 4 electrons. So that means the answer is B. The answer is B. So silicon has 4 valency electrons. And an intrinsic semiconductor at room temperature has, so a pure semiconductor, intrinsic means pure semiconductor. So a pure semiconductor at room temperature, we have discussed that at absolute 0 temperature, we have no free electrons and holes in semiconductor, right. There are no free electrons and holes, but it is said that in question they have asked about room temperature. Okay. So at room temperature is nothing but about 27 degrees centigrade. So at this temperature the semiconductor will have few holes and electrons, okay, few free electrons and holes. So the answer is A. And depletion region or depletion layer is caused by what? So depletion region or depletion layer is in PN junction diode. Yes, we have seen PN junction diode, right. So in PN junction diode at middle, so at the junction where the P type and N type materials are joined, okay. So there we have seen the depletion region. So why the depletion region is occurring? Why? Because the electrons from the N type are moving, are diffusing to the P type, okay. So that means what? Electrons from there are recombining with the holes in the P type. So depletion region is because of recombination. So that is B. So the answer is B. The depletion region is caused by recombination of electrons in N type with the holes in the P type. And see this question, depletion region contains what? So this was asked in previous MSc electronics entrance exam. So depletion region contains what? So what it consists of? It doesn't contain holes and electrons. Yes, depletion region is not having any carriers in it, okay. There are no carriers in depletion region. So what is there? There are ions aligned, right. We call that ions as space charge. We also have called that as barrier potential, right. Barrier potential, or we call that as space charge. So the answer is C. So the answer is C here, space charge region or depletion region. So we have ions aligned in depletion region. See this question, a little complex but very important. See here, a small percentage of impurity is added to an intrinsic semiconductor at 300 Kelvin. So which one of the following statements is true for the energy band diagram shown in figure? So how it is? So we have valence band and we have conduction band here. So the new energy level, that means they have doped a semiconductor with this some impurity, okay. We don't know what that impurity is. So we have doped the semiconductor with some impurity. The new energy level is this one, okay. The new energy level is near to the conduction band. So when the new energy level is near to the conduction band, that means there are free electrons in the material. So what is free electrons contribution element? That is pentavalent impurity, right? And when you add pentavalent impurity, what happens? The semiconductor will be n-type semiconductor. So you read the options. Intrinsic semiconductor doped with pentavalent atoms to form n-type semiconductor, or intrinsic semiconductor doped with trivalent atoms to form n-type semiconductor, and intrinsic semiconductor doped with pentavalent atoms to form p-type semiconductor, and intrinsic semiconductor doped with trivalent atoms to form p-type semiconductor. So the answer is A, because as the energy level, the new energy level is near to the conduction band, it is near to the conduction band, right? So that means you are adding pentavalent impurity. When you add pentavalent impurity, the semiconductor formed will be n-type. Okay? So the answer is A. So far we have discussed about semiconductors, and if you see, we are living in a era of electrons, okay, electronics. So the devices around us there are many electronic devices around us. We are using our mobile phones, we are using washing machine. Okay, washing machine is a combination of electric and electronic, so that is called as embedded system. Okay, so and we are using our personal computers. So these are all electronic devices. So you see you dismantle your mobile phone, or when you assemble, you observe what are the different electronic components which are present in your electronic device, okay, electronic appliances, and appreciate the fact that these are all have come from a common substance, which is sand. Okay, we have extracted silicon from sand, SiO2, which is very common substance. We see everywhere, sand everywhere. But after extracting, after doing some processing, that is doping and all, we are doing wonders with that sand, right, with that silicon. So if you touch with our mobile phone, you can make a call. If you touch, you are seeing some videos. If you touch, you are making some videos, okay, you are capturing some images. So these all can be done with this processing of that semiconductors. So sand is a very common substance with uncommon potential. So the assignment for you is, you study about the electronic appliances in your home and see what are the electronic components which are present there. Okay, so you use the damaged pieces, okay, don't damage the good ones. You see there, and happy learning, stay home and stay safe. Thank you.
पेश है दिन भर की बड़ी खबरें।